Good afternoon, student. So today I'm going to discuss, I think the last part from the syllabus that I haven't discussed with you is this representation theorem of open set. So this representation theorem of open set is how we represent an open set in the form of an open intervals. So what does it state? Every open set G of R can be written uniquely, means can be written only one as a countable union of disjoint open intervals. Which what does it mean? Means that every open set of R, subset of R, you can express it as a countable uniquely as a countable union of disjoint open interval, or you can say that as a union of open intervals which are countable and disjoint, pairwise disjoint. So here what we start with the proof is that let G be an open set in R. Okay, G is any open set in R, and let X be any arbitrary element in G. So since G is open, recall the definition of open set. It means that X is an interior point of G. So therefore, by definition of open sets, there exists an open interval instead of open ball. There exists an open interval having centered at X such that X belongs to that open interval Ix and is contained in G. Name it as equation 1. It follows straight away from the definition of open set. Now X belongs to G. It implies that from here X belongs to G, it implies that X belongs to Ix. So which implies that X belongs, obviously it will contain in the union of Ix, X belongs to G. Thus we have here, what is X? X is an element of G, and what does it imply? It implies that X belongs to union of Ix. So thus we have G is contained in the union of Ix, X belongs to G. Name it as equation 2. Also we have, for all X belong to G, Ix is always a subset of G. From here we have X belong to G, Ix is contained in G because X being an element of G, which is an open set. So it implies that X belong to Ix and Ix is contained in G. So this shows that union of Ix contained in G, and X here is any arbitrary. So the union of all those Ix in open interval will be contained in G. Name it as equation 3. So combining 2 and 3, we have G is equal to union of Ix. So this proves that that open set in R can be expressed. So this shows that G can be expressed as a union of open interval where each Ix here is an open interval. So this proves that an open set in R, here this is an open set, can be expressed as a union of open intervals. Now can we make this union or disjoint? Yes. Let us choose the largest among these intervals Ix. Let us choose the largest or the maximal of such Ix and call it Ix star. And how we choose this Ix star, which is the largest among this open interval Ix? Let us see here. You take alpha star to be the infimum of alpha. Suppose here you have alpha, this is point X, and this is point alpha, and then alpha 1 is some alpha prime is here, alpha double prime, and so on, such that we take this alpha star to be this infimum, that is the greatest lower bound, alpha 1, alpha double star, alpha double prime, and so on. So alpha star here will be among the greatest lower bound of alpha, that is alpha star is equal to infimum of alpha, where alpha here is less than X, such that the open interval alpha X must contain in G. Alpha X is contained in G. So here what is alpha star? Alpha star, suppose here this is alpha X and alpha star is somewhere here. Then you can take, how we choose this alpha star is that here you take alpha prime, the open interval alpha prime X, alpha double prime X, and so on. So therefore alpha star is the greatest lower bound, that is the infimum among this alpha 1, alpha prime, double prime, and so on. Similarly from here also to the left of this X also you take point beta, consider this open interval X beta. x beta prime, x beta double prime, and so on. B star double star here stands for the supremum, that is the least upper bound of this beta prime, beta double star, and so on. So therefore we have, similarly we take here beta star here is equal to the supremum of this beta greater than x, because beta, as you can see, it is greater than x, such that the open interval x beta is contained in G. So this is how we choose the maximality of this. So as you can see here, alpha star and beta star, alpha star is the infimum of this alpha prime, and beta star is the supremum of this beta prime, beta double prime. So let us take x star to be the open interval alpha star beta star. Okay, so we take this ix star to be open interval I star alpha. Clearly by construction, alpha x is, as you can see here in this, as you can see here, x is greater than alpha star, but it is less than beta star. So by construction, clearly this x lies between alpha star and beta star, so that x here belong to this ix star, the open interval ix star, and name it as equation 4. And on account of the definition of infimum and supremum, we can find that for every epsilon greater than 0, using the definition of infimum and supremum, so for every epsilon greater than 0, alpha star plus epsilon will always belong to the open interval alpha x, which is contained in G, and beta star minus epsilon will always belong to this open interval x beta, which is contained in G for some alpha beta. So therefore, for every epsilon greater than 0, we have alpha star plus epsilon belong to, because this is contained in G, so this implies that alpha star plus epsilon is contained in G, and beta star minus epsilon belong to G, which gives that ix star here, which is this one open interval alpha star and beta star, is contained in G. Using the definition of infimum and supremum, as we can see here, we have shown here that this belong to G and this also belong to G. So therefore this shows that each and every point which lies inside this will be contained in G. Hence for all x belong to G, x belong to ix star, and it is contained in G by combining 4 and 5. Because x belong to ix star G and it is contained in G, so combining these two, we have this. So this implies that G is equal to union of ix star, because as we have seen here, there in the beginning, how we express x as G as a union of open intervals, and we have here also that we can show that ix star is contained in G, so union of this is also contained in G, and moreover for every x belong to G, we have x belong to ix star, so G is also contained in the union of ix star. So this implies that G must be equal to union of ix star. So next we claim that this ix star, this open interval, they are pairwise disjoint. That is, for any xy belong to G, either ix star is equal to iy star, or ix star intersection iy star is an empty set. And to prove this, suppose here we prove it the other way, that is, suppose neither of these two are true. Means suppose that this statement are false, that is, suppose ix star is not equal to iy star and ix star intersection iy star is non-empty. So as you can see here, so if it is non-empty, means there exists a common element among these two. So this shows, though with ix and star and ix y star, they are distinct. So you consider this, draw this real number line, consider this with this pink one as ix star, open interval ix star, with point x is lying somewhere here, and then iy star is this, because they are non-empty, means there exists at least some point of which are common to both this interval iy and ix. So that this is the place, this is the common point, okay, between this interval ix star and iy star, and x is somewhere here. So therefore combining these two intervals, Ix star union Iy star. This shows that this Ix star and Iy star union Iy star will be a larger open interval which is greater than Ix star, because it will contain elements outside this Ix also. It will contain all elements of Iy star also. So therefore Ix union Iy star will be a larger open interval greater than Ix star, and which contain x. So this contradicts the maximality, because we have taken Ix to be the maximal. We have shown here that we have taken Ix star to be the maximal of the open interval which contain x. But what we have here is that there exists another open intervals, that is Ix star union Iy star, which still contain x, and it is greater than Ix. And why this contradicts the maximality of Ix star? Because we have assumed that these two statements, they are false. So hence they must be pairwise disjoint. So this implies that G is equal to union of Ix, x belong to G. It can be expressed as a union of pairwise disjoint open intervals. Obviously, due to the maximality of Ix star, this representation of G as open interval is also unique. How? Because suppose Ix star and Ix double star be two such interval, and if we take Ix star to be as the maximal, then Ix double star will contain in Ix. Similarly, if we take Ix double star as the maximal, then Ix star will be contained in Ix double star. So in fact, if we consider both of them as the maximal, then they are the same. So this gives us the uniqueness of this representation of G in the form of open interval. Now, last part we have to prove is that how many members are there in this, how many members of this maximal open intervals are there in the disjoint. Suppose here the pairwise disjoint family, that is collection of this family of open intervals Ix star, can be written as Ix star, comma, Iy star, comma, Iz star, and so on, where x, comma, y, comma, z belong to G. Then every open interval, we know that every open interval contains a rational. And since these open intervals, these open intervals, they are disjoint, means no two of them have a common elements. So therefore, the rational numbers which belong to this will be distinct from the rational numbers which belong to this, which will be distinct from the rational numbers which belong to this, and so on. So then there exists distinct rational numbers x cubed, y cubed, z cubed, just such that this x cubed belong to this rational number x cubed belong to Ix star, y cubed belong to Ix star, and so on. Therefore, we can associate each of these intervals with a rational number. So we can associate each of these with a rational number, and these rational numbers, they are distinct. And since we know that the set of rational number is countable, by countable means that either finite or countably infinite, that is, there exists a 1-1 correspondence between the set of natural number to this set collection. So this shows that each of these open interval can be associated with a rational numbers. So therefore, and this collection of our rational numbers is countable. So therefore, we have here, this implies that the family Ix star are open interval is again countable, because we can associate each of this family of open intervals with a distinct rational numbers, and the collection of rational number is countable. So this implies that this collection or this family of open intervals which form as the union, such that the union of this gives you the open set G, is countable. Therefore, G is countable union of pairwise disjoint open intervals. So hence the proof of the theorem, that is, every open set G of R can be written uniquely as a countable union of disjoint open intervals.